Hey everyone, welcome back to Trigonometry. This will be lecture 5 of the course, and in this section we're going to take a look at the graphs of sine and cosine. So let's go ahead and jump into that. And so I'm going to call this section 2.1 in the video series, the graphs of sine and cosine. And so far we've identified a number of key values for the sine function in particular, and I want to summarize those. So let's start by making a little table of the known values of sine. Okay, and so I've got my y equals sine of x up here, so this is what the value of the function will be, and these are the angles. So I'm just going to plug in a bunch of angles that we know. So 0, pi over 6, pi over 3, pi over 2, 2 pi over 3, 5 pi over 6, pi, 7 pi over 6, and 4 pi over 3. Okay, and I think, yeah, so might have to go on to another line here, unfortunately. That's okay. Just so long as we can get them all down on paper. So 4 pi over 3, 3 pi over 2, 5 pi over 3, 11 pi over 6, and 2 pi. Those are the ones that I want to focus on right now. Right, and so we've been through a lot of these, and we know the values. And so 0, 1/2, square root of 3 over 2, and 1. And then negative 1/2, negative square root of 3 over 2, negative 1. Okay, and so these are kind of looking like this. And then at 7 pi over 6, we've got negative 1/2, negative square root of 3 over 2. And then at 3 pi over 2, we've got another negative 1. And then negative square root of 3 over 2, negative 1/2, and 0. Okay. And so looking at these values, it may not be obvious what the pattern of the sine function is. And so this is where coming in plotting the function is going to be helpful. Okay. And so what I'm going to do is I'm going to basically plot these values on the x-axis, and these are going to be my y-axis values. These are going to be the value of the function that I plot. Okay. And so let's see what happens when I do this. Okay, and so we know actually that the sine function is bounded by 1 and negative 1. Right, so we can kind of truncate our y-axis a bit because we know it doesn't get outside of there. And then I'm just going to like put a few values on here. So I'm going to go every 2 actually. Okay, and so we'll say this is pi over 2, and don't worry about that one. And we'll say this is pi, and we'll say this is 3 pi over 2, and we'll say that this is 2 pi. Okay. Okay. And so when x is equal to 0, so again I'm just referencing the table that we drew up above here. When x is equal to 0, the sine function is equal to 0. When x is equal to pi over 2, the sine function is equal to 1. Okay. And then when x is equal to pi, the sine of x is equal to 0 again. And when x is equal to 3 pi over 2, the sine function is equal to negative 1. Okay. And then at 2 pi, it's back to 0. And so you can see that the function, the sine function, looks a bit like this. Okay. Right, and so in between 0 and pi over 2, you're going to have pi over 6. It's going to be right about here. It'll be about 1/2. And then you're going to have pi over 3. And at that point, it's going to be square root of 3 over 2, which would be right about here. Right, and so you can see all the values that are swept out there. So it starts at 0, it goes up to 1, back to 0, then to negative 1, back to 0. And I bet you can guess what happens beyond that, right? It just kind of repeats this pattern forever. All right, it just goes up and down forever. And this is called the sine. This is the graph of the sine function. Sometimes it's called the sine wave. Right, and that's what it looks like. It looks like a wave, and so it gets that name sine wave. Okay. All right. So, and of course, it goes in the opposite direction as well, right? It does go like this in the opposite direction. Exact same pattern, it just continues on in the other direction. Okay, so let's talk through this graph and kind of draw out some of the key characteristics of the sine wave, the graph of the sine function. So a few things to note. Okay. So the first thing to note is that the domain of y equals sine of x is all real numbers. We kind of knew that ahead of time, but this graph makes it plain that this can just keep going on forever. So the domain of sine is all real numbers. You could write it like negative infinity to infinity. That's another way to write it. So any angle can be plugged in, no matter how large or how negatively large. It doesn't matter. Anything can fit in there. And when you look at the graph here, it's very obvious that the range of the sine function is -1 to 1. You can see that it bottoms out down here at -1, tops out at 1, right? And so no values of y are ever met above 1 or below -1, right? So that's the range. The range of sine is, well, it's going to actually include -1, so -1 and include +1, right? So think of it as a closed interval, -1 to 1. Okay, and then the third thing to note here is the idea of the period. So I'll just write it out first, and then I'll talk to you about what it is. The period of y equals sine x is 2 pi. Okay, and we talked about period in a previous section, but we're going to definitely get into it in more detail here. So the graph is going to repeat indefinitely in both directions. We just saw that. The pattern that the sine function makes is going to repeat itself every 2 pi radians. Okay, and so let's just talk about that a little bit. Let's say we start here. When do we get back to here and headed in the same direction? So we go all the way up to here, and then we come down to here. Now we're back at 0, but technically we're headed down, so we haven't started over yet. Then we go down to -1, and we come back up. Right, and so this interval right here is one iteration of the sine function's period. And now you'll notice that when we start here, it does the same thing over again, right? So this is, each of these are 2 pi. So this goes from 0 up to 2 pi, and then from 2 pi, this would be 4 pi. Right? So that's what we mean when we say that the period of the sine function is 2 pi. It repeats itself after it goes 2 pi radians. Right, and this would be true no matter where you start. Now think about this. If I start here, then I go up, down, and then I start over. And from here to here is also 2 pi. So if I take 3 pi over 2 and I add 2 pi to it, then I'm going to get whatever this value is. Okay, and so that's the idea with the period. It doesn't necessarily mean that the period has to start at 0 and go exactly to 2 pi. It just means from any point on the graph, if you go 2 pi radians ahead of that point, you're going to be in the exact same position. Okay. All right, and then the last thing to notice here about the graph is that the sine function is an odd function. So y equals sine of x is an odd function. All right, it's an odd function. And what does that mean? Let's remind ourselves. It means that sine of -x is equal to negative sine of x. Okay, so for example, the sine of negative pi over 2 is equal to -1, which is equal to negative sine of pi over 2. Okay, now so here's sine of pi over 2. You can see that it's equal to +1. Now where would negative sine of, or sine of negative pi over 2 be? Well, it'd be right here actually, wouldn't it? This is negative pi over 2. And the value there is -1, right? And so that's what we're saying here. Sine of negative pi over 2 is -1. which is the same value. -1 is equal to negative sine of pi over 2, right? So it's just a little technicality about how the function works, okay, with the argument. Okay. And so this is the sine, this is the graph of the sine of function, and here are kind of 4 takeaways that you can immediately see when you look at the graph of the sine function, right? The domain, the range are obvious when you look at this. The period becomes obvious as soon as you kind of think about it for a moment. And then you can verify that sine is an odd function by looking at the graph as well. Okay. All right, so let's move forward here. So now that we've seen what the graph of the sine function looks like, let's talk about how the sine function can be used and how the graphs can vary depending on what's thrown into the mix. All right, so we're going to talk about how to graph variations of y equals sine of x. Okay. And so, in particular, we're going to look at all the variations that can appear of this form. So y equals a times the sine of bx minus c. Okay. So in the graph that we've looked at, b is 1, c is 0, and a is 0. So we've looked at the case where a equals 1, b equals 1, and c equals 0, right? And when you do that, you get y equals 1 sine of 1x minus 0, otherwise known as just sine of x. Okay. But what happens when these values are other than this? When a is like 2 and b is a half and c is maybe like something like 5 pi or something, right? So what happens when we have variations? Well, each of these numbers, a, b, and c, are going to they're going to provoke a certain kind of change to the stock sine function, right? And so the first one we want to study is what's called the amplitude. So we're going to go through each of these properties in turn. The first one we're going to start with is what's called the amplitude. Amplitude. Okay, so the graph of y equals sine of x oscillates between 1 and -1. So we saw that already. Y equals sine of x oscillates. That means it goes back and forth between 1 and -1. Okay. However, what happens when we consider something like this? What about y equals 2 times the sine of x? Okay, and so let's set up something like before, not as many values here, but y's and x's. And so let's say I have my 0, my pi over 2, pi, 3 pi over 2, and 2 pi. Let's just take those handful of values. What happens when I plug those in? So sine of 0 is 0. So 0 times 2 is 0. Sine of pi over 2 is 1, and 1 times 2 is 2. Sine of pi is again 0, and so I'm going to get a 0 here. And the sine of 3 pi over 2 is -1, so -1 times 2 is -2, and then back to 0. Okay, and so it appears as though plugging in this 2 in front of the sine is basically going to make the maximum values of sine larger and smaller, depending on how you're thinking about it, further away from the y equals 0 axis. Okay, and so let's draw a picture here. Let's say we have, okay, we'll stretch these out a little bit more. 1, 2, 3, 4. 1, 2, 3, 4. 4. 1, 2, 3, 4. Okay, and let's put these values on here. So here's 0. There's pi over 2. There's pi. 3 pi over 2. And 2 pi. Okay, and then let's say this is 1, and that's 2, and then -1 and -2. Okay. Well, so let's draw the sine function on here first. Apologies for being off screen there. Let's draw the sine function on here first, y equals sine of x without the 2. So it's going to start at 0, and at pi over 2 it'll be equal to 1, and then it's back to 0, and then it's negative 1, and then it's back to 0. So it kind of looks like this. Right, and it would keep going, etc. So this is y equals sine of x. Now what happens with y equals 2 times sine of x? Well, we've got the numbers here, so it starts at 0 again, and at pi over 2 it jumps up to 2, so it's up here, and then it's back to 0, and then at 3 pi over 2 it's down here at negative 2, and then back to 0. So it looks like this. Right, and that's y equals 2 sine of x. Right, and so you can see the difference here is that when we multiply by 2, the y equals 2 sine of x function it basically stretches the peaks, makes the sine wave taller, makes the peaks more extreme. Right, but you'll notice all the values in between also get stretched, right? The only values that don't get stretched are the 0 values. Everything in between is stretched out as well. Okay, so this is what we mean by the amplitude. The graph of y equals 2 sine x is amplified by the factor of 2, right? So by the factor of 2. So basically the values are all doubled, aren't they? Okay. Now, we call the absolute value of a the amplitude of the function. Okay, remember this is y equals a sine of bx minus c. Right, so this guy right here is the amplitude. Okay, so that's the amplitude. All right. The next item so A tells you the amplitude. The next item to discuss is what's called the period. Okay, so next we need to know what is the period. Well, we talked about the period. We know that the default period is 2 pi, but how can the period be changed by varying up how the function's written? So the period of the function is 2 pi by default, but consider this function. Y equals sine of 2x. Okay, and let's plug in some values here. So I'm going to have my x, and then I'm going to have a sine of x and a sine of 2x. We want to be able to compare these directly. So let's put in some values. 0, pi over 4, pi over 2, 3 pi over 4, pi, 5 pi over 4, 3 pi over 2, 7 pi over 4, and 2 pi. Okay, so a lot of values here. We just want to be able to compare them, and I'll tell you what all of these values are, but you could obviously go out and look at your unit circle cheat sheet and you'd be able to see what these values all are. But so you've got 0, 1/2, 1, 1/2, negative 1/2, negative 1, negative 1/2. Oh shoot, that's a 0, 0, negative 1/2, negative 1, negative 1/2, 0. Sorry about that. Okay, so these are the ones we're familiar with. These are sine of x. But what happens when I plug these values into the argument when it's 2x? Well, so think about what that's going to do. So sine of 2x, right? What if I plug in x equals pi over 4? Then I get sine of 2 times pi over 4, which is equal to sine of pi over 2. So pi over 4 plugged into this is the equivalent of pi over 2. right? And so what you'll find if you evaluate all of these angles in sine of 2x is that the values look quite different. So I get 0, and then I get 1, and then I get 0, and I get -1, 0, 1, 0, -1, 0. And so it looks like things are quite different here. It looks very dramatically different. Let's plot it and see what's actually happening here. Let's actually plot this. And we'll go like this. Okay. And let's put some of these angles on. So there's 0, and we'll say this is pi over 4, and then pi over 2, 3 pi over 4, and pi, and then 5 pi over 4, 3 pi over 2, 7 pi over 4, and 2 pi. Okay. Right, and then let's just say this is 1, and actually let's put up a little higher. 1 will be up there, and then this will be -1. Okay. So we know it starts at 0. Okay. And then at pi over 2, it's equal to 1. And then at pi, it's equal to 0 again. I'm talking about the sine function here. And then at 3 pi over 2, it's equal to -1, and then back to 0. Okay, and so this is what sine of x looks like. All right. Okay, so that's the sine of x. Now what about sine of 2x? Well, sine of 2x hits 1 a little bit earlier. So it starts out low, and then it actually hits the value of 1 here. And then at pi over 2, it's equal to 0. And then it's equal to -1 here. And then it's equal to 0. And then it's equal to 1, 0, -1, and 0. So let's draw that in. It looks different. It goes like this. So it looks like that, doesn't it? Right, so what's happening here? What's going on? What can we see here? Well, what's the period of the sine function? It starts out here, and then by the time you hit theta equal 2 pi, it's starting to repeat itself. Right here's where it's start back at 0 and heading up. Right, so the sine function, sine of x, has a period of 2 pi. So we already knew that. That's not news to us. Right? But what about the sine of 2x? What's the period for that look like? Well, it's the bold line here, not the dashed one, and it actually starts to repeat itself here. Right? And how many degrees have we moved through from here to here? Well, that's pi. So the sine of 2x has a period of just pi. Right, so the sine of 2x actually repeats itself more often. Another way to say it is to say that it's oscillating back and forth faster. Its period is shorter. Okay, and so by the time sine of x has done 1 period, sine of 2x will have done 2. Right, so its period is actually twice as fast. So the sine of 2x is going to complete 2 full cycles in the same time required for the sine of x to complete 1. Right? And this means that the period of y equals sine of 2x is half the period of y equals sine of x. Okay? Okay. So we say the sine of 2x has a period, so we say sine of 2x has a period half as long as sine of x. Right? So its period is completed by pi, whereas the sine function itself takes 2 pi to complete. Okay, so in general, then, if you're given y equals sine of bx, the period can be calculated as basically take the 2 pi, sort of the standard sine period, and you divide it by whatever b happens to be. Right, and so of course if you're just talking about sine of x, then b is equal to 1 and the period is 2 pi over 1. Okay. All right, so that's period, right? So we've got amplitude, which stretches the sine function up or down. And then you've got period, which makes the sine function oscillate faster or slower, as the case may be. And the third item is what's called the phase shift. The phase shift, right? And so for this example, let's consider y equals sine of x minus pi over 2. Okay. And so for this one, I'm going to again kind of generate some values and see what's going on. So we're going to consider, I'm going to make my table look a little bit differently here. We're going to consider x when it's equal to 0, pi over 2, pi, 3 pi over 2, and 2 pi. Okay, we're going to consider those values. Okay, and so over here I'm going to plug in y equals sine of x minus pi over 2. Okay, so when I plug in 0 here, I get sine of 0 minus pi over 2, which is just sine of negative pi over 2, isn't it? And that's equal to -1. If you look back at our first page, we did in fact see that value. Next, I'm going to plug in sine of sine of pi minus 2 minus pi minus 2. And that's going to give me sine of 0, which we know is 0. Okay. And third, we'll plug in sine of pi minus pi over 2. Okay, and that's going to be equal to sine of pi over 2. So pi minus half a pi is half a pi. Okay, we know that that's equal to 1. And then sine of 3 pi over 2 minus pi over 2 is equal to sine of pi, which we know is equal to 0. And then finally, sine of 2 pi minus pi over 2 is sine of 3 pi over 2, which we know is -1. Okay. Okay, and so then what does this look like when we plot it? Right, so let's plot these values here on the end. Okay, so let's draw this out again. So in this case, I'm going to need a little more. I have to go this direction, so that's negative pi over 2, and then I've got 0 here, and then I've got pi over 2, and then I've got 1, 2, 3 pi, and then so on. Oh, sorry, and then 3 pi over 2, and then 2 pi. Okay, right, and so on. We'll maybe go in that direction a little more, but. So let's start with the sine function. What's the sine function look like? The regular sine function. Well, if that's 1, and if this is -1, then the sine function starts at 0, and then it goes up to 1, and then back to 0, and then to -1, and then back to 0. Right? So the sine function looks like this, again in dashed. All right, that's the normal function that we're all used to. Right, and we know over here it kind of comes like this. Okay, now what about the sine of x, instead of the sine of x, the sine of x minus pi over 2? Well, we've got the values here. So at 0, this guy is equal to -1. Okay, and then at pi over 2, it's equal to 0. And then at pi, it's equal to 1. And then at 3 pi over 2, it's equal to 0. and then it's equal to -1 at 2 pi, right? So it starts out low like this and kind of comes up and then goes down, and then you can imagine it's going to come back up, right? And this is the sine of x minus pi over 2. So what has it done? What has the sine of x minus, what is adding the minus pi over 2 to the argument done to the sine function? Well, it's shifted it, hasn't it? Right? This point here, for example, has moved over to here. Right? And this point here, we'll say, has moved over to there. And you know, all of these points are just kind of shifted over. Right? So everything is kind of shifted, right? This guy went over here. And so the sine function the minus pi over 2, the minus c here, it doesn't change the period of the sine function. It doesn't impact the amplitude. What it does is it horizontally adjusts the sine function graph, slides it left or right. Okay. And so in this case, it slid everything to the right. Okay. Okay, very good. All right, so the period is unchanged. You know, we still see a full cycle complete, you know, in 2 pi. So here you can, looking at the solid sine of x minus pi over 2 function, you can see if we start here, then we're starting to repeat here. So the period is still 2 pi, right? It's just shifted over a little bit. Okay. So in general, this is what's called the phase shift, and in general, if we're given y equals a sine of bx minus c, if we're given that function, then the phase shift can be calculated using c over b. Okay. Right, so whatever c happens to be, you divide that by b, and that'll tell you what the phase shift is. Now b could be, if b is not equal to 1, then b can play into how the phase shift plays out, right? But if b is equal to 1, then it's really just c that is the phase shift. Okay. All right, so now we know about amplitude, which is the absolute value of a. We know about period, which is 2 pi over b. And we know about the phase shift, which is c over b. Right, so these 3 items are what goes into graphing y equals a sine of bx minus c. Okay. So now what we want to do is, okay, given that we know these values, how can we draw a reasonable approximation of a sine function? Okay, so what's the method? All right, I'm going to go through a very specific method here, and this will work almost all the time, right, for the sine function. And a lot of what we'll talk about later when we get to cosine and the other trig identities will fall back on this same method. So this is the method for graphing y equals a times the sine of bx minus c. Okay, step 1. First thing you got to do is identify the 3 quantities we just described. Right, so we need to identify the amplitude, the phase shift, and the period. Okay, and so we know that the amplitude, I'll just rewrite these, is given by the absolute value of a. The phase shift is given by c over b, and the period then is equal to 2 pi over b. Okay, so we need to identify these three numbers first. Okay, step 2 then is this method is going to use kind of what are called key points, right? And what we want to do is we want to identify 5 key points, right? And what are the key points? So let's start by saying we want to find the value of x. Find the value of x for 5 key points. Okay, and what are the key points? Well, x1, this is going to be the beginning of the cycle. Okay. x2, x3, and x4, right? These are going to equal the quarter point, the midpoint, and the 3/4 point of the cycle. And then, of course, the 5th number is the end point of the cycle. Right, now hopefully this isn't like, too nerve-wracking, right? All we're saying is we're going to have a beginning and an end. The beginning is going to be x1, the end is going to be x5. You're going to have a midpoint, which we're going to call x3, and then you're going to have a 1/4 point and a 3/4 point called x2 and x4. That's all that is meant by this, right? So this is the beginning, this is the end, this is the mid, this is the 1/4, that's the 3/4, right? Because if you're here, you've gone 1, 2, 3/4 of the way. That's why it's called the 3/4. Okay, so we'll talk specifically about how to identify these 5 points in a moment. Don't worry, we'll get to this in a second. All right, we're just kind of flushing out the general process here. Okay, the third step, once we've identified these 5 key points, is we need to evaluate the function at these 5 points. So we need to evaluate f of x at x1, x2, x5 at all 5 points. Step 4 is we're going to plot the points. Okay, and draw a line, draw a smooth curve through them. Okay, plot all the points and draw a smooth curve through them. And then step 5, if needed, we'll extend it in either direction. Right, because we're just plotting one period. We know the period goes on and on. We know that the plot goes on beyond just one period. And so if we need to, we can extend it in either direction. Okay. All right, so we're going to basically take these 5 steps, step 1, step 2, step 3, step 4, step 5, and we're going to do some examples now. Okay, and so the first example is going to be this one. We'll kind of start out easy. So we want to graph y equals 1/2 sine of x. Okay, so step 1 is to identify the amplitude, period, and phase shift. So the amplitude is the absolute value of 1/2, right? So remember, this is your a times sine of bx minus c. So you have to keep in mind that this is adhering to this form, and for example, we don't see a c here. That just means c is equal to 0, etc. So the amplitude is the number in front. It's the coefficient out here, the a, and that's 1/2. The period, well, it's equal to 2 pi over b, right? In this case, b is equal to 1. I have 1x. So it's just 2 pi over 1, so 2 pi. And then the phase shift, what's the phase shift here? Well, the phase shift is C over B, right? And so in our case, C is 0 and B is 1, so there's no phase shift. Okay. All right. And so let's go to step 2. Now we got to identify our 5 key numbers, 5 key points. So we'll start with the beginning of the period. We'll just set that equal to 0. Now we're going to find an x2, an x3, an x4, and an x5. And how will we do that? Well, what we're going to have to do is we understand that to go from x1 to x5 is 1 period, which is 2 pi. So what I need to do is I need to break 2 pi up into 1, 2, 3, 4 parts, right? 1, 2, 3, 4. And so what I can do is I can just use 2 pi over 4, whatever the period happens to be, divided by 4, and add it to the previous point. So the second point is just going to be 0 plus 2 pi over 4, which is just pi over 2. Okay. The third point will be pi over 2 plus 2 pi over 4, which is pi over 2 plus pi over 2, which is pi. And then, of course, pi plus 2 pi over 4 is 3 pi over 2. And then this will be 3 pi over 2 plus 2 pi over 4 equals 2 pi. Okay, now no big accomplishment here, right? We know the period hasn't changed, so this is just going to be the regular 0 to 2 pi. But just kind of showing you the method there. Whatever the period is, divided by 4, and you can generate these numbers by adding this to the 2 pi plus 4, and then this to 2 pi plus 4, that to 2 pi, right? So, all right. And so next, what we want to do is move on to step 3. Now in step 3, we need to evaluate the function at the 5 numbers. And so I'm gonna have a y1, a y2, a y3, a y4, and a y5. So y1 is going to be 1/2 times sine of x1, which is 1/2 times sine of 0, right? We found 0 to be our x1 here. Okay, and so we know the sine of 0 is 0, and so this is 0. The next one will be y2 is going to be equal to 1/2 sine of x2, which is 1/2 times the sine of pi over 2. And so we've got 1/2 times, now the sine of pi over 2 is 1, and so I get 1/2. Okay, then I get 1/2 sine of pi, which is 1/2 times 0, which is 0. And then I get 1/2 times the sine of 3 pi over 2, which is 1/2 times -1, which is -1/2. And then finally for y5, I get 1/2 times the sine of 2 pi, which is 1/2 times 0, which is 0, right? So here's my values of the function at the 5 numbers. Okay, so you could say I've got the following points to plot. I've got my x1 and my y1 now. And they are 0, 0, pi over 2, 1/2, and then pi, 0, and then 3 pi over 2, -1/2, and then 2 pi, 0, right? So these are the 5 points that I can plot in step 4. I'll just put that here. Step 4 is to plot these points. Okay, so let's actually plot those points and see what this looks like. And so let's say I've got, how you choose to space things out here is up to you. I'm just going to make that pi over 2, and then pi, and then 3 pi over 2, and then 2 pi. Okay, and so we know that this is gonna, if this is 1 and this is -1, then 1/2 is right in the middle. So it starts at 0, it goes up to 1/2, then it comes back down to 0, and then it goes to -1/2, and then back to 0. Right, so it looks like this. Right, and we could extend it in either direction as part of step 5. Extend if needed. All right. Very good. Okay. All right, let's take a look at another example. Okay, let's think here. Should we do one example or maybe 2 examples? Let's do 2 more examples of sine just to make sure that we have this. Let's kind of ease into some of these harder ones. So the next example, let's try to graph y equals 3 times the sine of 2x. And so here we're fiddling with the amplitude. We're also messing around with the period. So step 1, we've got the amplitude equal to 3. The period is 2 pi over b, which is 2 pi over 2. So this one is going to have a different period. And what about the phase shift? Well, the phase is going to be c over b, if you remember. So in this case, c is 0, but b is 2. And so it's 0. Okay, so here we've got a different amplitude, so the sine function is going to stretch out more. Instead of topping out at 1, it's going to top out at 3. And instead of bottoming out at -1, it's going to bottom out at -3, so it's more stretched out. It's also oscillating more rapidly, right? So a period is half as long as the original sine function. Okay. So that's step 1. Step 2 is we got to find all the values of x1 and y1. Okay, so we need to know what all of these values are. Well, we'll start at 0. Okay, it's good practice in general to just start at 0. Now, the period here is pi, so I need to break pi up into 1, 2, 3, 4 intervals, right? So it'll be 0 plus pi over 4. And then it'll be pi over 4 plus pi over 4. Okay. And then pi over 2 plus pi over 4. And then 3 pi over 2 plus pi over 4. Okay, and so again, we've seen this one before where we go from 0 up to pi, and the whole period is there, and we just naturally have those broken up. Okay, let's do step 3. Let's find all the y values. So y1 is 3 times sine of 2 times 0, which is, now this sine of 2 times 0 is just sine of 0, and so this is 3 times 0, so it's 0. y2 is equal to 3 times the sine of 2 times pi over 4. So that's really sine of pi over 2, isn't it? These will cancel, right? You get a cancel here. Sine of pi over 2 is 1, so this is 3 times 1. Okay. y3 is 3 times the sine of 2 times pi over 2, and that's going to be 2 times pi over 2, which is, the 2's will cancel, and it's just sine of pi, which is 0. y4, you can probably figure this out, is going to be -3, and y5, of course, is going to go back to 0, right? I encourage you to plug these values in and make sure that that's right, but you can usually detect the pattern after just 2 or so. Okay, so that's the way that works. And step 4 then is to go ahead and plot these things. Okay, so let's go ahead and try to draw this. And so we're going to 1, 2, 3, 1, 2, 3. So this will be 1, 2. Again, the scale is not important how you draw it, just so long as you denote what you're doing. But this is going to look an awful lot like a regular sine function because of the scale, right? Right, so we know it's going to kind of start at 0, and then it's going to go up to 3, and then it's going to go back down to 0, and then it's going to go to -3, and then back to 0, right? And that'll extend in either direction, right? What's important to notice here is that, this is pi over 4, this is pi over 2, this is 3 pi over 2, and then here we are at pi, and we've repeated ourselves, and the period is appropriately pi. Okay. It looks an awful lot like the sine functions we've seen, right? And I think really depending on, as long as there's no phase shift, it ought to look a lot like a regular sine function, just with a different scale. Either a different x scale and or a different y scale. Okay? Very good. All right, so let's do one more example. Let's introduce a phase shift in here and see what it looks like. Let's try this example. Let's graph y equals 4 times the sine of 2x minus 2 pi over 3. Okay, so this has an a, a b, and a c, so this will be about as hard as they get. Of course, they could get harder, but step 1 is to identify everything. The amplitude here is 4. Absolute value of 4 is 4. The period is 2 pi over b, which is 2 pi over, in this case, b is 2, so 2 pi over 2. So this one has a shorter period as well. And then the phase shift, I wrote that badly. The phase shift. What's the phase shift? Well, it's c over b. And in this case, the c is 2 pi over 3. And the b is 2. Okay, so what do I have here? I have 2 pi over 3 times, this is 2 over 1, so times 1/2. So the 2's will cancel, and this just is pi over 3. That's just dividing fractions there. So pi over 3 is the phase shift. Right, and then what I usually tell people is that this is a good place to start your period, right, that when you're plotting. So, this indicates where to start your period when plotting. Now, you can start the period anywhere. It's just that if you start it with pi over 3, it'll be 0, like you would expect from the sine function. Okay? Okay, so we've got this guy, we've got that guy, and we've got that guy. So what's happening with this thing? Well, it's been shifted over pi over 3. It's stretched all the way up to 4 and down to -4, and it's oscillating faster because its period is pi instead of 2 pi. Okay, so let's go ahead and come up with our numbers, our 5 numbers. So x1, x2, x3, x4, and x5. Well, we'll start at pi over 3, just because that's where a period is supposedly going to begin. Right, so if we start at pi over 3, then we just have to add pi over 4 to that, don't we? Because the period is pi, and we need to break pi into 1, 2, 3, 4 intervals. Right, and so the second number will be pi over 3 plus pi over 4. Now, there's a little bit of arithmetic you can do here. Basically, you get a common denominator of 12. I'll do the first one. So you're going to have 4 pi over 12 plus 3 pi over 12, and that gives you 7 pi over 12. Okay, and just that same exercise each time. So 7 pi over 12 plus pi over 4, right? And if you go through that, you'll find you can get to 5 pi over 6, and then 5 pi over 6 plus pi over 4. If you go through the exercise of adding those together, you'll get 13 pi over 12. And then 13 pi over 12 plus pi over 4 will get you to 4 pi over 3. Okay. All right, so then what does it look like here? Let's see what our y values would be. So here's x1, x2, x3, x4, and x5. And so you can see that everything's just shifted by 1/3 of a pi. So instead of starting at 0, we start at 0 plus pi over 3. And instead of ending at pi, we end at pi plus 1/3 of a pi. That's why you get 4/3 of a pi instead of 3/3. Okay. So what's our y1, y2, y3, y4, and y5 equal to? Well, y1 is, again, let's just write it all out here, 4 times the sine of 2 times pi over 3. That's the x1 there. Put it in parentheses. And then you have to do the minus c part too, so minus 2 pi over 3. Okay, and I'm going to just let you kind of think through what that would be, but this would be 2 pi over 3 minus 2 pi over 3. So this is really 4 times the sine of 0. And so, of course, you're going to get a 0. What happens here? 4 times the sine of 2 times 7 pi over 12 minus 2 pi over 3. Well, the arithmetic's just a little more involved here, but what you end up with is pi over 2 in here. And so this would be equal to 4 times the sine of pi over 2, which is 4 times 1, so 4. Right, and then you can go through the exercise, but what you'll find is that this is equal to 0, and this is equal to -4, and this is equal to 0. Okay, I encourage you to go through it, but in the interest of time, I'm going to just kind of skip to the values. So let's go ahead and draw this thing now. Let's try to draw this out and see what kind of trouble we can come up with. So step 4 is to plot the points. Okay, so step 4 is to plot the points. And so let's see here. Make sure I give myself 1, 2, 3, 4. It goes up to 4 and down to -4. Okay. And I'm going to just count everything out in terms of quarter pies. Okay, and so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Just put a bunch of these on here. And so it's going to start 1, 2, 3. It's going to start here at 0. And then 4 more, it's going to be 1, 2, 3, 4. It'll be up at 4. And then 4 more, it'll be back at 0. And then 4 more, it'll be down at -4. And then it'll be back up here. Okay. And so this here is pi over 3. And this is 4 pi over 3. And all the points in between here we can label. It's just important that you know where you're at. This will be 7 pi over 12. This guy here is 5 pi over 6. And then this one here is 13 pi over 12. Okay, so it just looks like that. Okay, and so this point here would be 7 pi over 12 comma 4. Actually, I think I wanted this to be in thirds, but okay, you get to understand. This would be 1/3. Oh, sorry, no, that's pi over 3. That's fine. Yeah, no, this is correct. This is what I wanted. Yeah. Okay. And so that's kind of as tricky as they get. Now, it really is just a matter of making sure you label these points in between here. Make sure you know what all of these are. Okay. Otherwise, you can kind of draw it anywhere you want. It's just a matter of putting it on the graph and labeling things. Right, but you can see this is definitely shifted over. Right, that's the key idea here. It's shifted over. Normally the sine is 0 here, definitely not 0 here, right? So it would go like more like this. This one is very off kilter, right? Obviously because of the phase shift of pi over 3. Okay. All right, very good. Let's move on. All right, so we've only talked about sine so far, and I think you may recall that the name of the lecture is Graphs of Sine and Cosine. Well, it turns out for the cosine, the graph is it's very similar. It's slightly different, but all of the discussion about graphing variations of cosine are going to follow immediately and identically what happens with the sine, right? So the graph of y equals a cosine of bx minus c follows the same basic pattern, except its cycle begins at 0. Cycle begins at 0, right? With cosine equal to 1. Right, so basically the graph of y equals a cos b of x, it's gonna have the same, it's gonna employ the same patterns as the sine function. So this will be the amplitude. This will tell you about the period. These two together will tell you about the phase shift. Same rules, 100%. The only difference is that the base cosine function looks a little bit different, right? And so let's draw it quick, and I think you'll see that's not a big deal. So let's start with, so this will be pi over 2, and then pi 3 pi over 2, and 2 pi. So I'm going to start with the sine function, actually. Okay, so it goes. So here's the sine function. I'll dot it. So that's the sine function. That's what the sine function looks like. Now the cosine function is just a little different. So cosine, if you remember, cosine of 0 degrees is equal to 1, actually. So cosine starts up here, and then it comes down to pi over 2. Cosine of pi over 2 is 0, and then cosine of pi is equal to 1, and cosine of 3 pi over 2 is equal to 0, and then cosine of 2 pi is equal to 1 again. So the cosine looks like this. Okay. So you can see it's very similar to the sine, it's just shifted over, right? So naturally here it would be coming down. And so it's a lot like the sine, except it starts at 1. Instead of starting at 0 and going up, it starts at 1 and goes down. Okay, other than that, all of the things that we've talked about with the sine function extend naturally to the cosine function. So let's do an example to confirm that. Okay, so here's an example. Let's graph y equals 1/2 cosine of 4x minus pi. Okay, or sorry, 4x, I'm going to write plus pi here. Okay. Now, something to notice here as you're looking at this, remember the form is a cos bx minus c. Now notice minus c. This is plus pi. So you have to be very careful, right? This is actually y equals 1/2 cosine of 4x minus, right, because the minus needs to be there, minus negative pi. Right, minus negative pi is the same as plus pi, right? So you can rewrite this so that it fits this format by just, instead of plus, put a minus negative. Okay, minus negative pi. And everything will work out fine if you do that. If instead you think of c as being pi, then you will be incorrect. You will be going in the wrong direction, right? Because this form says minus c, and this is plus pi, so you need to write it as minus negative pi. Okay, so step 1 is the amplitude. Okay, so a is equal to 1/2, no problem. What about the period? Well, the period is 2 pi over b, so that's 2 pi over, in this case, 4. So the period here is pi over 2. Right, so this is a much shorter period. This function is going to complete a period in 1/4 of the time as the normal cosine function does. What about the phase shift? Well, it's c over b, and in this case that's negative pi over 4. Okay, so you've got your three important features of the function, and so we can see that the graph is now going to oscillate between 1/2 and negative 1/2. The period is only pi over 2, and the graph is shifted such that a normal cosine period is going to actually begin at negative pi over 4. Right? So what that means is that at negative pi over 4, the function will be equal to, it'll be at the peak and headed down, right? Like the cosine looks like this, right? Right? And so what this is saying here is that this is negative pi over 4. So that's it's just a nice hint about where to start plotting the thing. Okay, step 2 then is to come up with our 5 numbers. So we need x1, x2, x3, x4, and x5. All right, so x1 is negative pi over 4. And then we just have to break the period of pi over 2 into 4 different intervals, 1, 2, 3, 4. So it might be useful to come in here and figure out what pi over 2 over 4 is. If I take pi over 2 and I break it into 4 parts, what do I have? Well, that's pi over 2 times 4 over 1. Or, sorry, times 1 over 4. This is 4 over 1, right? I invert and multiply. And so pi over 8 is what we want to add on. All right, if we add on pi over 8, then that'll create our interval. Okay, and so we start at negative pi over 4, and we add pi over 8. Okay, and if we do that, we get negative pi over 8. Okay, and then I have negative pi over 8 plus pi over 8. Of course, that's 0. And then 0 plus pi over 8 is, of course, pi over 8. And then pi over 8 plus pi over 8, well, that's 2 pi over 8, otherwise known as pi over 4. Okay, and so we start here, and our 5 points are given. Okay, and you can obviously see that pi over 4 minus pi over 4 minus negative pi over 4, that's going to give you your pi over 2 length interval. Okay. Step 3 then is to identify the y values that correspond to these x values. So y1, y2, y3, y4, and y5. Okay, and I'll just do the first one to show you how to do it, but y1 is going to equal 1/2 cosine of 4 times x1 plus pi. Okay, and let's plug all that in. So 1/2 cosine of 4 times negative pi over 4 plus pi. And what do I get there? Well, this is 0, isn't it? This is 4 times 4. The 4's will cancel, and then I got a negative pi plus a pi, and so that's 0. So this is 1/2 times the cosine of 0, which is 1. Okay, so we start at 1/2. Right? And you could do a similar exercise, and I encourage you to do so, but you'll see that this is equal to 0, and then this is equal to negative 1/2, this is equal to 0 again, and this is equal to positive 1/2. Right, so we start at 1/2, we go to 0, then a negative 1/2, then back to 0, and then back to 1/2. Okay, so we've got these 5 y values to plot. Right, and so these go together, right? That's an ordered pair. These two are an ordered pair. Sorry, that one goes to that one. Don't look at that. Never mind. What are the ordered pairs? Let's write them out. So we need to plot. So it's negative pi over 4, comma 1/2, and it's negative pi over 8, comma 0, and 0, comma negative 1/2, and pi over 8, comma 0, and then the last point is pi over 4, comma 1/2. Okay, so let's plot all of these points and see what it looks like. And so for this one, I think we'll kind of put it a little more in the center here. Okay, and we'll go back 2, forward 2. So we'll say that up back here is where we're up at the top, and then it comes down. It looks like this. And then at 0, right, this guy here is at negative 1/2. And then it comes back up, and then it's back at the top. Right, so this is negative pi over 4. This is negative pi over 8. This is, of course, 0. This is pi over 8, and this is pi over 4. And I should probably label the axis as well. This is 1/2, and this is negative 1/2. Okay, so you can see how it goes. Right, and then it's going to continue on in either direction. Now, notice this is shifted, right? Like this here was originally here, right? And so this point has been shifted all the way over to there, and this point has been shifted over to there. Okay, so that's the phase shift. All right, perfect. Okay, so I think that's where we'll end it. Again, cosine and sine, cosine follows all the same format as the sine. It's just that the base cosine function is plotted differently than sine. It's got a different start and end point, if you like. So we'll go ahead and stop there, and then next time when we get together, we'll talk about how to graph the other trig functions, so the tangent and the cotangent, and the secant and the cosecant. Okay. All right, so we'll leave it at that, and we will talk to you all next time. Take care.